Very cool. Thank you so much. So if you've been in this industry for any amount of time, you might have noticed there's a number of religious beliefs that we have within this ecosystem. And I'm going to start off kind of naming a few. And again, you might be familiar with these. You might have strong opinions on these. Vim versus Emacs. This has been a long going kind of, dare call it a feud between the two communities. But we definitely have some religion here, right? There's been some religion around Perl and Python. I think it's pretty clear who won that one. Well, maybe not, at least in science, though. Python has definitely taken off across the board. And we're seeing even now newer ones about shells, right? Bash versus ZSH. But I got to say, nothing has prepared me for for the Linux distribution religion and operating system religion that exists. So even though I've been part of operating systems and Linux distributions for, let's see, nearly 20 years now, it seems to have just gotten more heated over time. And so I'm going to be talking about a number of Linux distributions, as I'm also going to be talking about HPC. But just bear in mind, this is my background. No offense needed or intended to anyone who has a favorite operating system out there. They're all fantastic. Each one of them provide a very good tool or solution or use case that it really excels in. And yeah, so trigger warning is, I guess, how we can start this. So we're going to start talking about CentOS. Now, CentOS has been one of the most utilized Linux distributions in the enterprise. And I'm not sure if everybody knows this, but it actually emerged from a high emphasis of high performance computing. Not only myself coming at it from a high performance computing perspective, but Rocky McGaw as well, who built about 99% of the first version of CentOS, CentOS 3, before he unfortunately passed away. And he never got to see kind of what was to come from his work and from with CentOS. And there was others as well. True is another example, among others. And there's always been a huge interest and drive from the HPC community in terms of operating systems, in terms of where the entire industry and ecosystem is going. And I think that that's super important. But we're going to focus a little bit more on CentOS. So quick history of CentOS. CentOS came out of something called the Chaos Foundation. It was a project that I created to build a community-assembled operating system. CentOS was born out of that. After Rocky's unfortunate death and some board manipulation, we had some of the CentOS assets being taken out of the Chaos Foundation, which was a 501c3, and into private control. From that private control, big open letter went out to the community saying the community demands these resources and assets back. And we were back to a community project again. And then Red Hat acquired it. There has been no shortage of drama within the CentOS ecosystem. But I want to say that it prevailed because of the amazing engineers and developers and contributors that have always been part of this and contributed so much of their own time and resources. And we have them to thank for holding up the entire community, the entire operating system, and everyone who's been using it. And this is why it was always one of the most utilized enterprise operating systems ever. So we kind of ended off this slide and this history of with Red Hat owning and controlling the assets of CentOS. So this was going really great, until we get a notification that the CentOS project is going to change direction. And you can see from this announcement, if you actually go to the source of this, Google it and go to the source, you'll see that there is 717 comments and none of them happy. Not any of them were actually really excited about this. Part of this was messaging, but also part of this was the fact that CentOS, which we've all come to know and love over decade and a half, is now going away. It is end of life. And we are now welcoming kind of full effort and full focus now, instead of going on CentOS, which we understand very well, to CentOS Stream. Now, CentOS Stream is a great thing. Unfortunately, due to how this was messaged and how this was kind of combined with the end of life of CentOS, it didn't get the love that it really deserved. So let me talk a little bit about what this means. So this image came out of something called the State of Enterprise Linux, and it really describes how do we get to enterprise Linux and what are the different variants and everything look like. And you can see in red, kind of smack there in the middle, is Red Hat Enterprise Linux, but to the left of it is CentOS Stream, and to the left of it further is Fedora. So CentOS, what used to be behind Red Hat Enterprise Linux and stable as Red Hat Enterprise Linux was, is now in front of Red Hat Enterprise Linux as more of a developer branch, more of a preview of what is to come within Red Hat Enterprise Linux. And it kind of, again, it changes the direction. It now becomes a community area, a development group, almost like a branch in a Git repository, a development branch in a Git repository, where people from the community can actually contribute back into what goes into Red Hat Enterprise Linux, as well as seeing what's coming. And then other derivatives from this are beyond Red Hat Enterprise Linux. So it kind of begs the question, actually something I should mention, so I have a slide or an arrow here, is when we as rebuilds, like where CentOS was, we no longer get the packages from Red Hat Enterprise Linux directly, we now get them from CentOS Stream. But the question that always arises for me then is, why don't we just all use Red Hat Enterprise Linux? Why did CentOS and now other rebuilds and other options, why did that even exist? Why not just use Red Hat Enterprise Linux? And the answer is because it exists behind a paywall. A lot of people in the open source community who've contributed to this don't necessarily want to pay to get their contributions back. And so to kind of articulate this, I asked the question, should open source software always be accessible, right? Should we always have free accessibility to go and leverage software that an entire community has created? And I'm going to point at this a little bit while talking about the kernel. So there's been a lot of contributions and a lot of engagement with the kernel. If you haven't been following the Linux kernel development, we can't go back to the first commits in source code management from Linus, back in 92, 93 era. But starting at about 2.6.1 to 6.1.0, we can easily keep track because that's when Git started taking over in terms of management. And we can track well over 1 million change sets, and just about 24,000 individuals from over 2,000 separate companies have all contributed to what we know as the Linux kernel. On the right side, you can kind of see the breakdown in terms of what companies have contributed. I was very surprised to see, for example, that by the number of lines changed, Oracle is in the lead and AMD is a close second. Right? That's kind of remarkable. And that was, by the way, for most active going into 6.1, excuse me. But what you're going to see here is companies that are in sometimes friendlies to each other, but in other times they're competitors. And even though they are competitors, they are all contributing to a common good, to a common goal. And that is super important because this means that not only can their competitors get access to what a particular company or individual is putting out there, but the entire world can, the entire community can. And what guarantees this is the GPL, the General Public License. And it does so by basically saying that all of the source code that is put into a particular project is always going to be redistributed under pretty much the same license of what it was originally released on. So all derivatives are always also GPL. It's a little viral, but in a way it forces good behavior. So should open source software always be accessible? And I think the answer is yes. Now, should open source software be restricted in any way? And I'm going to say no. I don't believe it should be. But this always leads then to the next question, which is what about binaries? We talked a little bit about source code, but now what about binaries? Chapter 5 of the Comprehensive GPL Guide says that binaries are always completely legal to redistribute because they are derivative works of that source code, right? Red Hat agrees with this, but there's a catch. And this catch is if you do redistribute any of the packages that come with Red Hat Enterprise Linux, you end up breaking your contract with them. So again, behind a paywall. So companies are now kind of stuck with this idea, right? Should it be community? Should it be open source, or should we be focused on profit? And this is a difficult decision for many companies. And we've actually seen this now starting to be a bigger issue over time, where companies are trying to balance the community and open source side with their necessity to build profit and create business. And we're seeing companies that are pivoting, in many cases, existing open source projects that they've put out there, and they're pivoting them based on corporate need. To some extent, that makes sense, but what it does to the community is it puts an uneasiness, a lack of stability out there. And here's a few examples of projects and whatnot that have done this. And they're doing it for good reason, right? They have to make sure that they are managing the needs of the business to keep putting capabilities and resources into these projects. So it's a hard problem to solve, all right? And I've been there. I've done.
Boa tarde.
Sorry, there's somebody off mute. Okay, thought there was a question. So been there, done that, right? Those of you who have followed Singularity development, you may know I created Singularity at the Department of Energy. It was a complete community, right? The community was growing, it was thriving, it was doing wonderful. I left Department of Energy, I created a company, Scilabs. And in this company, we continued to grow and throw more resources into Singularity. And in terms of bringing more visibility to the company, I brought the Singularity source code into Scilabs. What happened then was very interesting. Even though Scilabs was growing at a remarkable rate, and we were putting more resources into the open source project, what happened was the community suffered. We started losing more and more open source contributors. We gained commercial contributors, of course, and the project did really well under that paradigm. But Scilabs did not continue to grow. And at some point, it was one of the hardest things I had to do in my career, as we had to resize the company, and the company shrunk considerably. To make sure that the open source project was always going to be stable, when I left Scilabs, I negotiated to bring Singularity with me. And thus now we have it back in the community. I was able to then also bring it into the Linux Foundation to ensure that it always stays community. And then the Linux Foundation just simply asked us to rename the project because too many things called Singularity. So we renamed it to Obtainer. Obtainer is what Singularity was always meant to be. It is a community open source project governed and led first and foremost by the community. Now, I made a vow in my career. I'm never going to make the mistake again of holding an open source project hostage. And thus the Rocky Enterprise Software Foundation was formed. I'm going to quickly talk about this, and then we're going to start talking a little bit more about why is this important to high performance computing. So the vision of the RESF, the Rocky Enterprise Software Foundation, is really focused on the problems that we had to solve around making sure that open source communities are stable, making sure that organizations can contribute to open source projects in a way that doesn't allow that company to hold that project hostage in a negative way, but also guaranteeing the stability of that project in a way that, honestly, that balance has never been struck before, in my mind, just right. And that was the point of the Rocky Enterprise Software Foundation. And we created the Rocky Enterprise Software Foundation to ensure that Rocky Linux stays stable. So going back to this real quick, this announcement that went out, I was one of those commenters. I posted something. If I would have known this would have gotten so much uptake, I probably would have written something that actually sounded somewhat better. But I put this out there, kind of spur of the moment, and it ended up with Rocky Linux. That's how Rocky Linux was born. We had over 10,000 people from that message join our HPC, Next Generation Slack, in less than 2 months. And we started seeing companies and organizations and other foundations and groups all starting to kind of come and work alongside of this. And as soon as we got the release out, adoption went through the roof. HPC is even higher adoption than the rest of the ecosystem, as Hyperion Research has shown here. And I do have a question, though. For all of the academia that's out there, I don't get this number, but maybe at some point somebody can explain to me why academia is not migrating off of an end-of-life operating system, but we can talk about that another time. If you know, send me a message. I'd love to have visibility there. Okay, so Linux has become the foundation of high-performance computing, and that's why I spent so much time talking about this. If you look at the top 500, right, there's some interesting trends and some interesting milestones that appear over this, right? So anybody remember ASCII Red? Well, I'd ask for a show of hands, but I can't see anyone. Hey, Steve, thank you. ASCII Red, it was one of the first big systems that broke the barrier. But look at the dates, right? So Roadrunner as well. But here now we've got exaflop, and we just surpassed exaflop with Frontier. But there's a couple big milestones here. First off, it's actually kind of interesting to me that ASCII Red and Roadrunner, even though they were kind of the breaker of the different levels of what we were going for, you can't even see how much of an impact that they have, right? Because it's dwarfed by how gigantic Frontier is. So the Beowulf was founded in 92, 93-ish time period. And this was the advent of Linux and the focus of Linux in high performance computing. This was the first time, to my knowledge, that people really started thinking about Linux and open source in terms of high performance computing. And that was what made the Beowulf so revolutionary and so amazing. And by the way, I'm this old. That's when I started getting involved in high performance computing through biochemistry and bioinformatics. So let's look at the Beowulf, because this was a really big and kind of massive change in terms of high performance computing. And by the way, I think it was around 2005 where that arrow starts, was the first Linux-based top supercomputer in high performance computing. That was the first time we got Linux, and it's been Linux ever since. So Linux is critical in terms of high performance computing. So Dr. Sterling and Dr. Becker, you may know those names pretty well. These were the creators of the first Beowulf. I don't know if this is in fact the first Beowulf picture, but I scoured the internet trying to find it, and I think it is. You can even see the sign off to the left that talks about the Beowulf. I think this was the very first Linux Beowulf that existed. And this completely changed the paradigm of how we think of high performance computing. At a high level view, this is the architecture, right? You have a control node, you've got storage, you've got a private switch. That control node is dual home. So you got one network going out to, or one internet connection going out to the network. You got one going to your private LAN. That private LAN is connecting to not only storage, but a whole bunch of compute nodes. And this is kind of the basic architecture. So again, you're going to see the control nodes, you're going to see storage, and you're going to see compute resources. Now, over time, this architecture has increased, right? It's gotten more capable and more complicated. All right, here's another example. And again, I just found these on the internet in terms of how people are building Beowulf architectures. And here's another one, right? But we see similarities, even though this is getting more complicated, right? We still have our control nodes, we still have our storage, and we still have our compute nodes. So even though it's a more complicated architecture, it's still a Beowulf at heart. This is a system I did have a hand in building. As I mentioned earlier, I spent a long time at the Department of Energy, Berkeley Lab, joint appointment to UC Berkeley. And this is the UC Berkeley system, Savio. At least it was when I was there. And this is a much more complicated architecture, but is it still a Beowulf, right? We still got our control nodes, still got our storage, and we still got our compute. Networks are a little bit more complicated, but the general architecture is still Beowulf. So Steve mentioned Werewolf. So here's my Werewolf plug in terms of how can we build these systems at scale, right? So you can start off with pretty much any operating system you want, any distribution. You can containerize those distributions or those node images. From that, you import that into Werewolf. From that, you roll that out to your supercomputers and to your clusters. Werewolf really helps with that, but that's from a system administration perspective. What about from a user perspective? right? What is the early, like going way back to even before the Beowulf, kind of what does the system usage guide look like, right? Of course, it's a simplified version, but these are the general steps, right? You SSH into your nodes, you research, understand your storage configuration, you download your source code, you compile your source code, you upload your data, right? Profile, test your applications, research your resource manager, queue configurations, and how do you need to work with that? Submit your jobs to the resource manager, monitor job execution, validate your job output. Okay, finally, you're downloading and moving your data back out and you're logging out. That's kind of the process of how we've been doing supercomputing from a user perspective. You know, again, kind of early on. How has it changed? It hasn't. We still do exactly the same thing, even on these different architectures that I've demonstrated. It's still the exact same process. So for almost, actually even over 30 years, before the Beowulf, our architecture hasn't changed. Now we've done some things to start to make this easier. And something, you know, again, I'd ask for raised hands if we were in person, but, you know, a lot of people are now starting to move to open on demand. And open on demand is a fantastic way to encapsulate that entire Beowulf architecture and give it to the user, back to the user as a HTTP web-based interface, right? And we've seen a lot of fantastic progress in terms of lowering the barrier of entry to high performance computing through projects like Open on Demand. But I challenge one aspect of this, which is, what is the user process? We've made it easier, but it's still pretty much the same 12 steps, right? There's a little bit of optimization here, but it's not really significantly changing that barrier of entry. It's making it graphical, yes, so it's helping, but we still have a very complicated workflow for users to be thinking about. All right, so what about containers? Has containers shifted this at all? Right, we've now been able to containerize our workflows. We can now move our workflows pretty much anywhere, right? But what is the use case around containers, right? Well, we might be able to get rid of number 3, right? We may not have to build the containers if they already exist, but if they don't exist, we have to build those containers. And building those containers are not necessarily, it's not necessarily an easy thing to do. So we still have to build those containers. But the general usage guide is again the same. Now, Jupyter has now changed this. We've now seen a huge leap in terms of making life better for researchers and developers through Jupyter, right? You can do a lot of different things with Jupyter, web-based interaction, web-based development, moving data and whatnot. It's lowered the barrier. We're seeing schools leveraging this in classroom now as well. Jupyter has really shifted this. And we finally are seeing kind of the steps changing now with Jupyter. But the problem is that Jupyter doesn't really meet the needs and architecture of general high performance computing. So we're starting to see a mismatch there. As a matter of fact, there's a number of organizations that I know of, number of HPC centers that have their traditional HPC system on one side, and they've got their Jupyter system on the other. The Jupyter system is running Kubernetes and kind of enterprise-focused technology, while the HPC side is still focused on traditional HPC. We haven't merged these very well. But wait, what if you run Open on Demand plus Jupyter? Now, all of a sudden, we are able to start merging these a little bit better. And again, here's some documentation that I found online from FSU, and they are absolutely doing this. And I know a number of different sites that are doing this, but what we've just done is we've recomplicated the process for users, right? We've not made this necessarily easier. We've added more steps and they're a little bit different. So right now, we are sitting at this point of transformation. We hear this term a lot come up, usually by management or CIOs or CTOs, but we're at this point of transformation. And I believe that this is being exacerbated by not only technology that's coming from enterprise, but also the need of job diversity is increasing. We're seeing different types of jobs coming into high performance computing environments, different types of use cases. different kinds of needs that the high performance computing teams are trying to solve. And in many cases, we're solving it by saying, here's a traditional HPC architecture. And this may technically solve some of the issues. It's not solving all of the issues. And it's definitely not lowering the barrier of entry. And so I'm going to end the presentation and the keynote and then open it up for questions if there are any, on foreshadowing a little bit about what's to come. And there's going to be some workshops tomorrow where this is going to be discussed, but we've been working on a project called Fuzzball. And you may have heard a little bit about Fuzzball at this point. I described Fuzzball in a series of buzzword compliant phrases, things like cloud native, things like hybrid, things like federated. And what it is exactly that. It is a cloud native federated computing architecture. What this means is you can have clusters on-prem, you can have multi-prem, you can have clusters in the cloud and multi-cloud. You can even have them in multiple availability regions in multi-clouds. And you can federate and stitch them all together. And you can create a single interface, a single API to allow users, to allow researchers, to allow pipelines, CI/CD, et cetera, to all leverage this gigantic distributed architecture. And we've been working on this now for over 2.5 years. We were originally funded to go and build this and to develop this. Here you can see a few screenshots from the interfaces that we have. Of course, there's a CLI, but CLI screenshots don't ever look good in keynote presentations. But you can see on the left side, you can see the creation of various workflows, how work jobs and volumes are all stitched together. It supports MPI, it supports GPU, FPGAs. It can go and seek out various bits of hardware. So if you have a particular GPU requirement, but you don't have one of those available on-prem, it can go to the cloud. If it can figure out where is the cheapest and best place to run that job based not only on resource and architecture availability, but also on cost and also on data. Where is that data? Things like data locality, mobility, gravity, and data security. So we can start figuring out very logically, where is this job going to run? And we can abstract all of that in a way that just makes it super easy for users. All right, so on the left side, you can see a graphical environment for creation of the job DSLs, the workflow DSL. On the right side, once you submit that, you can get various analytics and various data about each portion of that job and what it's doing and how is it working. On the bottom left, you can see a list of all the different jobs running. And on the bottom right, you can even jump into a particular job that's running and get an active shell. And all of this is over API. There's no SSH or anything involved in any of this. So that is what we've been kind of foreseeing as the next generation of, or at least an option of a high performance computing architecture. And what does the usage guide look like? Well, you log in. If your containers don't already exist, you got to build those containers. And then you build your DSL, you build your workflow, or you leverage someone else's workflow that already exists and you templatize that workflow, create an application around that workflow, and then you just run it. And the entire goal of everything that this is doing is to enable science. So that's where I feel as though we need to be thinking longer term in terms of our entire industry. How do we drive science? How do we lower the barrier for high performance computing? How do we expand the types of workflows, the types of jobs, and the types of capabilities of what high performance computing could do today? And how do we take advantage of additional architectures, resources, and infrastructure? Things like cloud, multi-cloud, GPUs, wherever that architecture, whatever those resources exist, how do we leverage that? So this is the first time I've ended a presentation, not only early, but on time, but actually a little bit early. So I'm leaving this open for questions. I don't have the capability to see if there's questions asked, or maybe I do.
That's okay, I got you. So we do have our first question in. Fuzzball uses any scheduler? If yes, which one?
Fuzzball uses a schedule. Actually, I don't have an architectural diagram in this deck. I apologize. Fuzzball uses a game theory engine for doing scheduling. It is a microservice within the microservice platform called Fuzzball Orchestrate that we have. There's 3 portions of Fuzzball. There's Fuzzball Substrate, which is kind of like your node-specific execution daemon. There's Fuzzball Orchestrate, which is a microservice platform in itself, and that is what schedules and manages a single Fuzzball cluster of substrate instances. And then you have Fuzzball Federate, which sits on top of all of that. Fuzzball Orchestrate and Fuzzball Federate both have scheduling capabilities within them, and it is not based on an existing scheduler.
Okay. As we wait for other questions to come in, I know both Chin and Axel have been nodding their head throughout your presentation. I'll open it up to either Axel or Chin if they want to add any kind of commentary or questions from their point of view.
Yeah, I think the first thing is, of course, it's fantastic that somebody finally does something about usability of HPC. Believe me, I've been ripping my hair out. I've been involved in everything from even the predecessors to Beowulf to this, and it's terrible. So I laud you and I comment you for really for the entire science community. Please accept my sincerest thanks to do that finally. That's part one. The second part is more a comment on GPL, and I can tell you I've been ripping my hair out on that one too. I understand where you're coming from and the reasoning behind GPL, but let me give you one example that really threw me off. So we were developing some hardware, in fact, a crypto processor, and we wanted to use PF, which is GPL. And of course, that would have required us to create an open source version of our PF version that would have disclosed pretty much all of the secret hardware that we put in that we didn't want to disclose. And as a result, we couldn't use PF in PF Sense. We had to use Open Sense with our own stuff that replaced PF. So, GPL in general, I love it. I think it's the right thing to do. But in some cases, when it forces you to disclose what the hardware does, it may not be the right thing. And it was for us a lot of work and a lot of money that we spent on rewrite.
I'm completely in agreement. I use the GPL as an example of why in some cases it's good to guarantee the redistribution of source code. But for example, the Rocky Enterprise Software Foundation, we use non-copyleft licenses by default for that reason. I've been involved in now 2 companies that's diligence on either an acquisition or funding was halted due to complexity, because there was some portion of GPL software that tainted something either in their infrastructure or product, and there had to be rewrites and whatnot. And it's a very complicated thing for especially a younger company or a company that's trying to innovate and develop something new. I mentioned that the Rocky Enterprise Software Foundation was really focused on not only the community side of this, but also making sure that we're doing the commercial side properly. And I don't feel as though there's been really a great balance between this so far, right? There's a lot of great foundations, open source foundations out there. Nothing negative towards them, but I don't feel as though that balance has been struck in such a way that makes it very valuable to bring in assets of a company to these foundations, because they lose complete control to the point where they're basically public domaining them in a matter of speaking. And most companies don't want to do that. They don't necessarily want to control it, but they want to have some advantage at least with that code, because they're the ones developing it. They're the experts at it. And I don't feel as though that balance has been made very well. And the Rocky Enterprise Software Foundation really focuses on trying to solve that issue. And again, this is why we don't release things under a copyleft license. So it is non-GNU, it is non-GPL. So we usually use BSD 3 clause or MIT.
Excellent, thank you. One question that came in from Sumit is expected date of launch of Fuzzball.
So we did a soft launch at Supercomputing where we're opening up to people who want to have early access to it. We have a number of early access usage on it, but it has not been completely GA'd as you saw. We are expecting the GA to be in later this quarter, early next quarter, and then for Federate to come out the following quarter. So we're getting very, very close. It is working. I think tomorrow they may even do live demos and scenarios with Fuzzball. I'm not sure. I'm not doing those demos, but that may be happening. So check that out tomorrow. Come tomorrow to the workshops.
Awesome. And someone would like to post you to post a link to the fuzzball orchestration design if you can.
Oh, I don't have that leak handy. We
Yeah,
don't have a huge amount of data. So reach out to me directly and I will. And I think Chin also, you were raising your hand too.
Yeah, Chin's got a few things. Chin, you're up. What would you like to say?
Oh, just want to follow up Greg's talk about balancing. So personally, and my team do contribute to freeware, but we only do it. Don't call me selfish. We only do it when it helps our business. As to our own software, it's completely commercial. So you can see that we are active contributing to, say, Ubuntu, the best storage benchmark. Okay, I love storage. I contribute to it. And then the other question is about computing. Let me also say this. People ignore the fact that starting from 2016, the world's data growth is accelerating. So moving data is very, very important. The scale of the data in modern sciences, such as biopharmaceutical science, is astounding. Okay, for instance, the photo counting CT each day creates about 60 terabytes of data. The healthcare, life science, IT people just shocked. Okay, they can't deal with it. So we are in a stage where computing and data movement are two sides of the same coin now. You cannot just talk about computing without talking about data movement. And so the data inertia is really true terms now. The third one is about scheduler. You know, people here know HPC a lot. You know, none of the parallel file systems, such as, say, IBM Spectrum Scale, Lustre, or BGFS, WekaFS, they use a scheduler to run, because true parallel applications do not need scheduler. They should have their resources sitting, their own queuing system in place. They don't need like a Slum and all that. Okay, that's what we do too. So scheduler and the HPC are not synonyms. That's what I like to emphasize. A true, well-written, high concurrent distributed HPC software do not need schedulers. So they can collaborate with schedulers. However, then that's the comments I'd like to make so far.
Thank you. Thank you. I'm not sure I can dispute or comment on any of that. I know from a scheduling perspective, this has been a critical need of high performance computing, but not necessarily driven by the storage, but driven by the resource limitations and capabilities on HPC systems. So meaning the scheduler is required to make sure that we're not oversubscribing the hardware on the compute side. I agree with you on the storage side. It's not my area of expertise, but definitely on the compute side, the scheduler is needed just to make sure, again, we're not oversubscribing hardware and we're making sure that the right jobs hit the right types of hardware. Chin, I'd love to hear your take on that.
Oh, sure. Because you see, containers actually are not really good for IO intensive operations such as data movement. That's why you see, for instance, at NERSC, you have dedicated DTNs, ESNAC, even the fast data knowledge base. We'll talk about DTN specifically, okay? So IO intensive ones, HPC actually is a misnomer. I hate to say this because a lot of people would ambush me when I go on the street, okay? There is also high IOs too. So, and the IO aspect of the HPC is very, I would say, poorly understood or misunderstood, because the storage vendor keeps saying, oh, this parallel file system provides you X terabytes per second data throughput. Give me a break, okay? Put it into any node that connects with a 1 Gbps node. You get the X terabytes per second in a 1 Gbps LAN connection? No way.
Chin, you may need the trigger warning on your talk more than mine. I agree with you. And I think that there's some cases where containers may actually help this. I think I'm at the top of my time, but I want to respond with one thing that I didn't mention on this talk, but I've mentioned in the past. Singularity and Aptainer use a single image file format for that container, which was designed to be optimized for parallel file systems. Parallel file systems, as you know, do very small file I/O, poorly, generally speaking, and larger file I/O very efficiently. So what we were able to do by having a single file container is to coalesce all of the small I/O into that one metadata operation, that one container file. And when running at scale, we can actually see pretty significant speed ups of launching particular applications that typically start off doing a lot of small file I/O, because again, we're coalescing all those small file metadata operations into a large single metadata operation, and then looping that back on each compute nodes through the loop device, which again coalesces all of those small file, all that small file I/O. So again, we've seen pretty good speed ups on that, but I'm not sure that I would call that data intensive, because typically that's part of the container, which is more on the operating system side and less on the data side. And it does make me wonder, is there a way that we can be using a similar technology for data intensive work, and managing and optimizing that?
The topic is probably too extensive to be discussed during in such a casual manner. I have plenty to say, in fact, okay? Since you were a creator of a Singularity, let me just tell you, we were really harassed by Singularity when we competed in the Supercomputing Asia 2019 Data Mover Challenge, because it didn't support the proprietary license mechanism. So we have to spend about 2 weeks to get around that, okay? And for an Olympic level competition, 2 weeks is so precious. And but you know what? No complaints. It's a good system. Thanks for creating it.
So real quick though, it's BSD, it's not GPL. You could have made the whole thing commercial.
Well, our software is commercial, and we don't have time to tinker with Singularity. We just force ourselves to spend 2 weeks, get around Singularity's constraint, because NSCC, the National Supercomputing Center of Singapore, decided to run Singularity in user mode. So there's no way we could get our license to work.
I get you. Well,
but thanks for creating it. It's a nice system.
Thanks, Chen. Greg, great presentation. Thank you very much.